Hey Bobcats, it's Mr. Peterson. Um, Today we're going to again continue looking at factoring quadratic functions. And our learning goal is to be able to find the roots of quadratic functions, but today we're going to be taking a slightly different stab at it. We're going to be looking at using the difference of two squares and perfect square trinomials to help us factor. So before we do that, we have two vocabulary words. Go ahead and write those down. You might already know them. Binomial is a quadratic expression with two terms. Trinomial is a quadratic expression with three terms. All right, so there's these things called the difference of two squares and the perfect square trinomial, and this is another way that you can factor certain situations, and it's kind of like this is where it pays to be observant, because if you can notice these kinds of patterns happening, it makes the factoring a little bit easier to do. So this is just a slightly different way to do these. The first one is the difference of two squares. And I'm going to copy this and paste it onto this slide. Make it a little bit smaller. There we go. All right, so our first problem, example 2a, is 9x squared is equal to 1. All right, so what we have, first of all, we want to rewrite this so that it's 9x squared minus 1 equals 0. Because remember, we want these things to equal 0. So we take 1 away from each side. And what we should now notice, possibly, if you're being observant, you notice that, hey, 9 is a perfect square, x squared is a perfect square, and 1 is a perfect square. And since we are subtracting them, we can use the idea that this is the difference of two squares. And what that says is a squared minus b squared is the same thing as the quantity of a plus b times the quantity of a minus b. All right? So in this case, our a, we need to think, okay, what number would we need to multiply by itself to get 9x squared? And the idea is here, if we did 3x, if we did that by itself, times itself, it would wind up giving us 9x squared. So we're going to write the second one over here. And then since we're subtracting 1, well, the perfect square for 1 is just 1. So we have a 1. And so what we notice here is that it's just going to wind up being plus, and then minus, plus, and then minus. And if you want, it's a good idea to check. Go ahead and check, make sure you did it right, and you'll see how this property applies here. There's our 9x squared, which is what we needed. Here's a negative 3x. Here's a positive 3x. And here's a minus 1. And of course, the positive and the negative 3x's cancel out, leaving us with 9x squared minus 1. So again, kind of an idea here, it pays to pay attention to help you factor these things. And you can notice, hey, this is the difference of two squares, so I can apply that here. Okay, another similar situation happens with the perfect square trinomial. And I should have this on there, but I don't. Let me go ahead and copy that picture onto that slide so we can compare as we go through. All right, so it's 40x equals 8x squared plus 50. All right, so we want everything to be on one side of the equation. So I'm going to take away 40x from both sides, and I'm going to wind up with 0 is equal to, I'm going to write it in descending order, 8x squared minus 40x plus 50. All right, and since we've got a trinomial here, we're gonna be looking to see, okay, can it fit into either one of these forms? Can it fit into either one of these forms? And you might notice that, hey, we're subtracting right here, so it's a good bet that it's probably going to be that top one. All right, but before we can go there, let's do a little bit of making this easier. We should notice that they all would have a common factor of 2. So what we're going to do is we're going to factor a 2 out. So that would be 4x squared minus 40, no, not 40, what am I saying? Minus 20x plus 25, and that of course equals 0. And then I can get rid of that 2 by dividing both sides of the equation by 2, and I get 0 is equal to 4x squared minus 20x, oh, I forgot my x up there, plus 25. All right, so now you can definitely see we're doing an a squared and then a minus a 2 times an a times a b, and then plus a b squared. All right, so here's what we need to be thinking, okay? What is our A? What is our B? Well, in this case, you need to ask yourself, what would you need to multiply 4x squared by to give you 4x squared? Excuse me, I said that wrong. What do I need to multiply by itself to get 4x squared? And the answer would be 2x. If I square that, it would go back to equaling 4x squared. And then what would you need to get 5 to multiply by itself to be 5 squared? Well, that would 25. That would be 5. All right. So that's our A and our B. Our is 2x and then a 5. Now you might be wondering, Mr. Peterson, why does the 20 play into this? Well, it's actually minus 2, and if we factor a 2 out, we've got a 10x, and at times a is 2, so times another 2, which means we have a 5x left. So that's where we get the 2 times a times b from. All right, so in a nutshell, what we have here, kind of going the long way, we have, when we notice that this is happening, we can say, okay, this is really just the quantity of 2x minus 5 squared. All right, and always a good idea to check it, make sure you did it right. Really, that's 2x minus 5 times 2x minus 5. We get 4x squared minus 10x minus another 10x plus 25. And then we have 4x squared minus 20x plus 25, which is what we have right there. So, and we haven't even solved it yet. We need to solve it. So they're the same factors. So we have 2x minus 5 equals 0, plus 5 on both sides, and we get 2x equals 5. Divide by 2. X is 5 halves, and since it was squared, the other one's going to be the same, so that's what's called a double root. You have a double root at 5 halves. You have a double root at 5 halves. All right, so that's that. Why don't you try this problem and try this problem? All right, we'll see you in class.